Sorry, folks. I had my recording bar block off my ability to expand my PowerPoint. So, weird, awkward start. Alright, so this is going to be Chapter 2. We're going to talk more about atoms, a little bit of history. It's actually kind of a fascinating history with atoms, with many sort of, we know everything now, and then we find out we don't. Which is kind of the story of science. Really, a scientist should always be ready to be wrong, and doing science is a process of being wrong until you finally aren't wrong, and then you go and try to find another way to prove yourself wrong. And that's science. I leave the learning objectives in. You can always check out those if you're wondering where these things connect. So the atoms were first proposed by the Greek. It was a Greek idea in 384 BCE, Aristotle. All matter is composed of 4 elements, and all matter is continuous, not atomistic. So that was back in the element days. If you're talking about the Greeks and European tradition, it's the 4 elements. If you're talking about most of the other world, including, for example, China, India, etc., it would be the 5 elements. And most cultures had similar elemental traditions. These are not the elements of today where we talk about the periodic table and elements. So atomos, which would be the point at which matter can no longer be subdivided, was actually proposed in about 450 BCE. I'm going to do a terrible job pronouncing these names, but because they are Greek, and I never do it right. So Lycopus and Democritus were the 2 main proponents of this. You will notice that is 450 BC. This is 384 BC. And so these ideas were around for decades before Aristotle. And he was a big proponent of, no, this is not right. Okay. Okay. So Lavoisier, again, French, not a great French speaker. Lavoisier, with the law of conservation of mass. So this is early 1700s. The law of conservation of mass is that during a chemical change, matter is neither created nor destroyed. Now, I want you to kind of build these ideas up in your head. So, atomos. We can subdivide matter over and over and over, and at some point we get to a point where we can no longer subdivide that matter. Atomos meaning indivisible. Okay. Now, as we know nowadays, it isn't actually literally indivisible when we get down to atoms. But what atoms are is that if you divide it any further, you get nothing that even resembles the materials that we work in every day. You get some very fundamental particles, which are very different than what you would think of as the matter around you. And so, again, we have the law of conservation of mass. For most of you in modern society, this is going to be, well, duh, Dr. Clausen. But remember that most of your ideas and what you think of as being the baseline of what you're experiencing with the world and how the world works, these ideas are actually built off of these philosophers and these scientists from earlier. And so, when you're talking about the law of conservation of mass, you can neither create nor destroy matter. So if we start with 100 grams of matter, we're going to end with 100 grams of matter. That matter has to be located somewhere. It could be turned into gas, in which case it escapes our control and goes off and gets vented in the atmosphere. But it still is going to be 100 grams of matter. Okay. So Lavoisier, this is the overall law of conservation of mass. So here we have 100 grams of mercuric oxide. If we were to take that mercuric oxide, have it undergo a reaction in which we would separate the mercury and the oxygen, what we would get is 92.61 grams of mercury, which is this little gray vial. And then we would get, if we could go ahead and control that oxygen and keep it in a balloon so it doesn't disappear on us, we would get 7.39 grams of oxygen. If we don't control it, of course, it vents off and then we can't get it back because the atmosphere is open and gas can drift freely everywhere it wants to. And this is where some people get the sort of misconception, have problems with the law of conservation of masses. Oftentimes they lose things. Doesn't mean that it's not conserved, it just means that you've put it somewhere else. Alright, now Proust, the law of definite proportions. So the law of definite proportions is a compound always contains the same elements in certain definite proportions. Now, funny enough, 1799, right? So it should be quite well spread. But there's something kind of amusing about this one in the fact that people still don't know this widespread. This knowledge is not widespread. Greenpeace for decades has had a thing on their website talking about how carbon monoxide from a automobile, carbon monoxide from a human breathing out, carbon monoxide from cows, and carbon monoxide coming out of the rainforest are different things. That the carbon monoxide coming out of the rainforest is somehow okay and natural, and the carbon monoxide coming off of a human or the carbon monoxide coming off of a car is somehow damaging and toxic. All carbon monoxide is the same definite proportions. It's the same elements arranged in the same way. And so all carbon dioxide has the same properties. Same chemical properties, usually same physical properties. There can be very slight differences, which we're not going to really get into here. If you would like to talk about that, you would need to get a little bit more advanced in chemistry. But when it comes down to it, they really just have the same properties. And so, for example, global warming, I'm not going to get super into that right here. But global warming, people oftentimes talk about the theory of global warming, and the theory of global warming has, of course, CO2 as being a major component of the greenhouse gases, and any CO2 is all the same, okay? The CO2 from a car, the CO2 from a plant, the CO2 from a person, they're all the same. They contribute the same. It's just the amount that each contributes. And so this is actually the law of definite proportions. So regardless of the source, your copper carbonate always has the same composition. And here we actually see three different sources. They look a little bit different, but this is because they're arranged differently. Here we have a nicely smoothed out rock. It looks very beautiful. And it has different banding that we can see. And over here we have a crushed powder of it. And you can see that changes how it absorbs the light a little bit, but it's the same compound. And over here we actually have the copper carbonate from copper being exposed to the atmosphere. In case you're ever wondering, by the way, the Statue of Liberty actually was a copper brass statue. And it used to be a beautiful golden color. She didn't always used to be that green color. That's actually because she's corroded. Same as this roof. This would have been a beautiful, like, sort of reddish, goldish color usually. So Proust, the law of definite proportions again. So Berzelius experiment illustrates the Berzelius experiment, illustrates the law of definite proportions. And so what he did here is combined two elements in several different amounts to see how this worked out. And so, for example, we put 10 grams of lead, 1.55 grams of sulfur, and we get 11.55 grams of lead sulfide. And this lead sulfide, this always has the same formula. And so if we maintain the same amount of one of these ingredients, it can only combine to give us that same amount of lead sulfide. Any excess is just going to be left over because it can't combine. And so, for example, like you buying hot dogs and buns, right? If you buy 6 hot dogs, 6 buns, you're getting 6 hot dogs with buns. If you buy 8 hot dogs and 6 buns, you're getting 6 hot dogs with buns, right? That's the same thing we're looking at here. And so here we got 10 grams of lead, we have 3 grams of sulfur, and again, because we only have 10 grams of lead, we can only make that equivalent amount of lead sulfide. And so we can only make 11.55 grams of lead sulfide. All the extra sulfur is just leftovers. It's not going to be able to react, at least not with this lead. And so again, we repeat that with the 1.55 grams of sulfur. We put that with 18 grams of lead. And what we see is we still only make 11.55 grams of lead sulfide. And we end up with 8 grams of lead left over. And again, this is just like our hot dog example. In this case now, we bought 6 hot dogs. We got 20 hot dog buns. We're still only making 6 hot dogs with buns. We don't get more hot dogs just because we have more buns. And so it's the exact same situation here. We just have one of these ingredients being limiting, and it has a formula: hot dog with bun or hamburger with 2 pieces of bread on it. That always comes out at the end, right? So John Dalton and the atomic theory of matter. This is 1803. John Dalton. The law of multiple proportions. Elements may combine in more than one set of proportions, with each set corresponding to a different compound. And so this right here is your law of multiple proportions with a little bit of a demonstration. And so we have dinitrogen oxide, and dinitrogen oxide has 2 nitrogens, 1 oxygen. Here we have nitrogen monoxide, 1 nitrogen, 1 oxygen. And here we have nitrogen dioxide, and this one's the nitrogen with 2 oxygens. Now note, by the way, that these compounds here are typically referred to as NOx, in case you're ever wondering. That's the NO with an X, meaning some variable. And for example, this is what you would typically see when you're looking at like smog, nitrogen dioxide. That's John Dalton, by the way. He's one of the ones that has Olivier and him have nice pictures that have been recorded, and were fairly famous during their day, so they typically make their way into books with their pictures. Some of the other ones do not. They just don't have good pictures that were recorded at a point in time. So all matter is composed of extremely small particles called atoms. All atoms of a given element are alike, and they differ from atoms of any other element. So for example, you have the atom, the element carbon. You could have 1 atom of that, or you could have many atoms of that. We have the atom, that's the element oxygen. Same thing with copper, and that's what we know as the periodic table. So the compounds are formed when atoms of different elements combine in fixed proportions. And that's where we get to things like CO2 or H2O. That's what you're actually saying. You're saying they're proportions that make up that specific compound. A chemical reaction is going to involve the rearrangement of atoms. So for example, when we burn, for example, coal, we would be burning carbon. That's a reaction of carbon and oxygen. It's going to give off primarily CO2. If you burn it very clean and you don't have a lot of other stuff in the coal, you'll basically just give off CO2. If you burn something like a gasoline, then that's going to be carbon and hydrogens. That's going to react with oxygen, and that's going to give you water, H2O, and CO2. So isotopes, this is the thing I sort of hinted at before, where CO2 has basically, it has the same chemical properties no matter what you're looking at. It has almost the exact same physical properties, but very, 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 very small amount of difference. The difference I was actually referring to is isotopes. So much of John Dalton's atomic theory has actually been modified to this day. There was not a lot that we could keep without small modifications, but the overall theory is still actually quite good and was quite visionary for its time, really. So John Dalton assumed that all atoms of an element are alike. He, of course, did not understand what an existence of isotopes. So that's the thing he was missing. And so isotopes are going to be atoms of the same element, but they'll have a slightly different mass. So a mole is going to be the number of atoms that's in 12.011 grams of carbon-12. That number, that is a mole. You can think of it a bit like a package of eggs, okay, or a package of something. So the number that corresponds to a mole of something is 6.022 times 10 to the 23rd atoms. So if you have 6.022 times 10 to the 23rd atoms, you have 1 mole of something. This is often referred to as Avogadro's number. And this number is kind of a weird number, you might have noticed. It's not real round. It's 6.022, weird fraction, right? And then it's times 23. Who uses a 23? But the reason for this number is actually the one that corresponds and creates the ability of grams here to match up with atomic masses. So for example, here, this is an atomic mass, carbon-12. That number is the same on the periodic table as the number of grams for a mole of that substance. I know, it's a cool trick they played. It's kind of weird, a little trippy. But what they did was they took this number, Avogadro's number, 6.022 times 10 to the 23rd, and that is actually a number that would correspond to creating grams from atomic masses. And so that's a mole. Again, I said a mole was like looking at a package of something. So if I say I have a dozen eggs, well, that's 12 eggs, right? And so when I say dozen, I know that that's the number 12. When I say I have a mole of atoms, I have 6.022 times 10 to the 23rd, an Avogadro's number. When I say I have a mole of pennies, I'd have 6.022 times 10 to the 23rd pennies. That's a lot of pennies, by the way. If I had a mole of molecules, I would have 6.022 times the 10 to the 23rd of them. The mass in grams of 1 mole of a substance, this is called the molar mass. This value is going to be the sum of the atomic masses, and that's the masses of the atoms, of the elements in a compound. So a compound, again, is the combination of elements to create that compound, that substance that is a compound of elements, if it were. And that's actually where the name comes from. It's compounding elements, right? So, for instance, the molar mass of water, which is a compound, is 18 grams. This would be, i.e., 18 grams per mole. So if you have 1 mole of it, you have 18 grams of it. That's that equality, which is then taken in. This is what it's represented as a molar mass of that water. So again, this is that moles and Avogadro's number and how they're related in a handy-dandy little graphic that's kind of pretty looking. It's just what I said before. So again, the number of atoms or molecules in a mole is an Avogadro's number. The mass of the element or compound for a mole of it is the molar mass. And this would be typically in grams per mole. This number here is the number of atoms or molecules. And then moles is just like saying I have 12 dozen of something. I have 144 of those things, right? If I have 2 moles, I would have 2 times 6.022 times 10 to the 23rd. Or another way of saying that would be 12.044 times 10 to the 23rd. That would be 2 moles of that. So, out of chaos, we got the periodic table. It actually was created, a few different people created it from a few different sources. Some of them were more or less than what we got right now. Dmitry Mendeleev is probably the most unique story of this. This is 1869. Mendeleev actually arranged the elements in the order of increasing atomic mass. He actually left gaps for yet undiscovered elements, which was sort of his big thing that set his apart from most of the others that were actually created during this time. Again, there was actually a number of periodic tables that were all created nearly at the same time. It was questionable whether they knew each other were creating them. Dmitry Mendeleev was sort of the best lasting. And kind of the most useful in terms of scientific discovery, because he very nicely identified, hey, there's probably an element right here. If you discover it and it matches up to what I predict, then it proves that it gives a nice evidence to support this. He also predicted the properties of those elements, of course. When those elements were eventually discovered, many of his predictions were actually found to be surprisingly accurate, actually. This is what his periodic table looks like. Now, for some of you, you may have connected 2 points, isotopes and this. And if you connect isotopes and this, you realize Dmitry Mendeleev could not have actually been correct. He actually had to have been a little bit off, a little bit wrong. And so it has been revised since then. So again, the properties of germanium has an atomic number. These are the properties of germanium right here. Mendeleev predicted what he called Ika silicon, which is essentially that below silicon. And this is silicon, like computer chip silicon. Just slightly different spelling for the day. Anyways, this was his predictions for it. 72 atomic mass. Then the modern periodic table, that's what that would look like. Atomic mass is right down here. The density predicted at 5.5. Dirty gray color. That would have this formula for the density of the oxide, and this formula for the boiling point of chloride. Many of you will probably look at this part and go, what in the world, Dr. Clausen? Why is he doing things for an oxide and chloride of this? In the day, this was actually sort of the easiest way to measure these things, is you would fully burn it, and so that would give you an oxide that you can then measure nicely. Or what you would do is you would boil it in chloride. And in fact, there's actually kind of a really funny historical documents involving the maid for, I think it was Adam Pope, who has all these complaints about the funny smell from the boiling of chloride, and how she's constantly getting into fights with her boss about cleaning out the chloride flasks, and how she refuses to do it. Which, fair enough, it'd be really, really unpleasant. Think of bleach or like a really bad pool. That'd be your chlorides. So, very, very amusing actually writing, where you go, oh, these were real people. Yeah, sure, they discovered great science, but man, they made their poor people that needed to clean up after them, they made their lives miserable. Anyways, so atomic mass, the observed, this was germanium was actually found in 1886. Germanium is actually the name of the element that is below silicon. That is 72.6 for the atomic mass. The density was found to be 5.47. The color was a grayish-white color. That's not too far from dirty gray. This was actually the formulas for them, and this right here was the boiling point of the chloride, and over here was the density of the oxide. And both are pretty close, actually. Did a really good job. Mendeleev really was close with his predictions, considering that he was working off of some assumptions that really weren't quite right, but they were good enough, and they mostly matched what ended up being. So really, really amazing job, really smart, really cool. If you want a really kind of interesting read, there's actually some like biographies about Mendeleev, and he's a very interesting individual. There's a lot of interesting history around him, actually. I won't go too far into it because I'm already going all off the topic. I always have to stop myself from that. I'm bad about that. So atoms, these are real and relevant. I know that you cannot see them, I cannot see them, but they are what compose the entire world around you. They are why things happen the way they do. So atoms are a very real concept. It is actually possible to observe computer-enhanced images of atoms. We have actually been able to see atoms now. It's a very complex, very expensive process to do it, but there is actually video now of atoms moving around in a molecule. It's very indirect how you have to do it, so I'll warn you about that, but it's kind of interesting. It's pretty cool looking. So let's talk a bit about the different types of chemistry. Oh, in case anybody was wondering what the big difference here is, you'll notice that the modern periodic table is actually organized by what's called atomic number. In the day, Mendeleev would have had no way of knowing that, even if it was a thing. The atomic number is actually the number of protons in it, and we'll get more into that. But suffice to say, it's not the mass. This is the atomic mass. You can see that mass number is larger and different. And so one of the problems with Mendeleev's periodic table actually was the fact that isotopes exist. Isotopes are actually slightly different masses for the same element. So Mendeleev would have actually had elements that would have been ranges of masses if he knew about isotopes and could actually do anything about them. But it wasn't something he could really do much about, and really he wouldn't have been able to do any better at the time anyways. It wasn't for another 20 years, 30 years that atomic numbers and breaking apart the atoms to figure out what was inside became a thing. So yeah, did really good for his time. Green chemistry. This means replacing rare or hazardous substances with more abundant or less hazardous substances. You probably hear your parents say stuff like this, or your grandparents say stuff like this, but like, it hasn't really improved since back in the day. Stuff back in the day was just made better, that sort of stuff. And there's some truth to that. Like, if you take a hot plate that was made 50, 60 years ago, way before my time, and actually break that thing open, that thing had, like, what would now be probably $100 of copper in it. These things were ridiculously built. They were built to last, but part of it was it just wasn't in as high demand, so the materials were cheaper and easier to get. Nowadays, if you tried to build hot plates and heating elements and you used all copper, my goodness, you couldn't afford to produce enough for all the people that want to buy them. It wouldn't even be close. It'd be crazy. And so a lot of what the development has happened in the last 50, 60 years isn't necessarily about making hot plates heat faster or hot plates heat better. It's more about doing things like replacing materials with cheaper, easier to produce ones, making it so that the stuff that goes into them is less hazardous, so when it does eventually break, it doesn't poison people. For example, replacing all the places where mercury was has been a huge hassle. And then after that, cadmium was a big thing. That was a poison that was going into people's drinking water. And so, it isn't always done right. And even if we talk about less hazardous substances, when it comes down to hazard, dosing is a big thing. So really, if you think about it like this, if we could perfectly make it so that everything broke down into heat, that would be the best possible thing we could ever do. But if we released enough heat, we'd boil the planet. So no matter how benign something is that we make it produce, if we make enough of it, it can overwhelm any system, right? And so green chemistry has very much been a thing for quite a while now, about 50, 60 years. And it's just a continuously evolving process where we tweak over and over and over to make these substances less hazardous, easier to make, more abundant, cheaper, faster to make, so we can replace them easier, last longer sometimes, but lasting longer usually doesn't do you a lot of good because there's sort of limits on how long something will last no matter how well you make it. Just due to the fact that people will lose it, people will damage it with impacts and stuff that are beyond the scope of what anything should ever do. Like, consider your phone. I don't think your phone has ever probably completely broken down. Most people's phones never actually break down completely. But eventually, something like you running over it with a tractor happens, or it sliding out into an ocean and then you not being able to dive down 1,000 feet happens. So, at some point, making it better just doesn't do. One of the examples of green chemistry is, of course, going to be the replacement of mercury fluorescent light bulbs. So those are replaced then with mercury-free light bulbs, and nowadays mostly these are LEDs. Though interestingly enough, there's their own problems with certain colorings of LEDs, and those leaching out semi-poisonous materials. Somewhat hazardous, but only hazardous because there's so much. But the fact that the LEDs last so long has really helped with that. So it hasn't been something just horrific. It's going to be a very, very long-term problem that really won't build up very fast. We'll be able to figure out pretty easily. But the mercury-free light bulbs was a big thing because mercury light bulbs were actually very problematic. Mercury has a bad habit of getting places it should not be, and then oxidizing, creating a much more poisonous form of mercury when it's in your water sources and in the wildlife around those water sources. Okay, that is the chapter 2. I'll go ahead and post chapter 3 sometime fairly soon. Hopefully that was interesting and you got something from that. Please let me know if there's any questions at all. I can expand on different topics, or I'll probably be posting some videos talking about some different questions that people are starting to have issues with once I start getting more responses. That'll really help. You have a great day.